we're going to look at another timeline. As discussed in our previous module, we categorize Western history into three phases: the classical, the medieval, and the modern. To recapitulate, the classical era concluded in 476 CE, and the medieval era ended in 1453, leading us into the modern period, commonly referred to as the early modern period in historical discourse. We talked about the Reformation, highlighting its profound impact not only on the Church but on European society as a whole. This epoch was characterized by decades of religious warfare between Catholics and Protestants and Protestants and Protestants, a conflict that echoes even in contemporary times. Although not as overtly violent as in the past, this conflict persists. The inherent futility of religious wars is that victory is impossible without complete eradication of opposing beliefs, a scenario rarely feasible or desirable. During the 17th century, this futility led to the emergence of a group of intellectuals we will refer to as philosophes, who rejected organized religion, specifically Christianity, in favor of seeking an understanding of the world beyond divine revelation. This ideological shift marked the beginning of the Enlightenment, a movement that endeavored to comprehend the world without the intervention of a deity, focusing instead on science as a means of discovering truth. Science, fundamentally, is the systematic observation and recording of nature. It involves measuring natural phenomena, recording these measurements, and formulating hypotheses based on them. This scientific approach signifies a shift from seeking truth in religious texts to deriving it directly from nature. Consequently, understanding this truth relies on human intellect or reason, hence the Enlightenment being termed the Age of Reason. To illustrate how science came to dominate our understanding of nature, we will trace advances in cosmology, the study of the structure of the universe. Ancient civilizations, such as the Roman Empire, observed celestial movements but did not perceive any motion of the earth, leading them to conclude that the earth was immovable and that celestial bodies revolved around it. This was the basis of the geocentric model, where geo from the Greek geis signifies earth. Around 150 CE, the Greek philosopher Ptolemy sought to mathematically validate this geocentric view. However, the observable retrograde motion of planets like Mars, where they appear to reverse direction temporarily, posed a challenge to the geocentric model. Ptolemy addressed this by proposing that while planets orbit the Earth, they also follow smaller epicycles, accounting for the observed retrograde motion. Despite the mathematical validation of this model, its accuracy was eventually challenged. For instance, inaccuracies in the calendar, based on the observed motion of planets and crucial for religious observances, called for a revision of the understanding of the universe's structure. This task was undertaken by Copernicus, a cleric from Bohemia, who proposed the heliocentric model with the Sun, not the Earth, at the center of the universe. This model not only rectified calendar discrepancies but also explained retrograde motion without resorting to complex epicycles. The model called into question the Church's official geocentric view, but was accepted as an explanatory framework rather than a scientific reality. When we look at the sky, we can identify stars by their relationship to others, like what we call the Big Dipper. The illusion helps us understand the sky, but we don't really believe there is a large serving spoon in space. Galileo Galilei, an Italian mathematician, further advanced this understanding. Tasked with improving the aiming of cannons, he conducted experiments on motion, leading to what we know as Galileo's laws. What Galileo found was that it is possible to scientifically predict the path of an object in motion, among other things. Galileo arrived at his findings using observation and experimentation rather than speculation, laying the basis for the scientific method. What Galileo essentially did was raise science to be a new standard of truth that was independent of dogma or ideology, setting in motion what we call the scientific revolution. His use of a telescope, originally a tool for merchants, allowed him to observe celestial phenomena, providing empirical evidence supporting the heliocentric model. This observational approach marked a significant departure from the speculative methods of his predecessors and laid the foundation for modern science. Galileo's letter to the Grand Duchess Christina of Tuscany, written in 1615, was a significant document in the history of science, particularly in the context of his conflict with the Catholic Church. This letter is notable for its defense of the Copernican heliocentric model of the universe and its attempt to reconcile science and scripture. The Church largely supported the geocentric model of the universe. This view was seen as being in accordance with certain interpretations of the Bible. In contrast, the heliocentric model, initially proposed by Copernicus and supported by Galileo's observations, placed the sun at the center of the universe. In his letter, Galileo argued for the compatibility of the heliocentric model with the Bible. He suggested that Scripture was written from an earthbound perspective and was intended for spiritual instruction, not as a scientific text. Therefore, apparent contradictions between scientific findings and the literal interpretation of the Bible should not be seen as undermining faith. Galileo advocated for a non-literal interpretation of the Bible in cases where its text conflicted with demonstrable scientific facts. He believed that God had provided humanity with senses and intellect to understand the world, and that Scripture and the natural world, as God's creations, could not contradict when properly understood. The letter was not well received by the church authorities. It was seen as a challenge to the established interpretation of the Scriptures and the Church's authority in matters of cosmology. The controversy around this letter and Galileo's continued defense of heliocentrism eventually led to his trial by the Roman Inquisition in 1633. At the trial, Galileo was found vehemently suspect of heresy for supporting heliocentrism and was forced to recant his views. He was sentenced to house arrest for the remainder of his life. According to a popular legend, after recanting his support for the heliocentric model, Galileo allegedly muttered the phrase "eppur si muove," or "and yet it moves," referring to the Earth's motion around the sun. This phrase has become emblematic of the tension between scientific truth and institutional authority. There is no contemporary evidence that Galileo actually said this phrase at his trial. It appears to be a later addition to the story, serving as a powerful symbol of his commitment to scientific truth despite the forced recantation. Galileo's and Copernicus's works were condemned by the Church, and as far as the Vatican was concerned, the scientific revolution was over. Despite this, the scientific revolution continued, especially in Protestant Northern Europe, culminating in the publication of Isaac Newton's Principia Mathematica. This work established Newtonian physics and represented a significant intellectual shift from a religious to a scientific basis of understanding reality. In 1992, after years of investigation and deliberation, Pope John Paul II formally acknowledged the errors committed by the Church tribunal that tried Galileo in 1633. The Pope noted that the judges who condemned Galileo had failed to recognize the formal distinction between the Bible's spiritual teachings and scientific statements. He clarified that the Bible does not explain the details of the physical world, a misunderstanding that was at the root of the Church's conflict with Galileo. The impact of science as a foundation for truth is undeniable, yet it is not without its challenges. The reliability of scientific evidence can be undermined by doubt, as seen in historical instances like the tobacco industry's response to evidence linking smoking to cancer or contemporary debates on climate change. This highlights the critical need for rigorous and trustworthy scientific inquiry. Please proceed to answer the questions in the assignment on Canvas. If you have any questions, you can post them in the open forum discussion or contact the professor using Canvas email.